We are almost at the last segment of this chapter. The topic is known as imperfection in solids. As the name itself suggests, the imperfection, that means it is not perfect. The question is why so? The reason is that unfortunately the word perfect hardly exists in our cruel world. In the case of solid also it is the true case. The solid state that we have learned so far is almost 95% correct. But in some of the cases, but in most of the cases rather I would say, the solids can have some kind of defects. Because an ideal crystal can only exist at 0 Kelvin. But as we know, the room temperature or the temperature in which we are used to is not 0 Kelvin. And not only that, since the crystals are closely packed in a dense environment, there can be some deformity or the missing of particular ions or atoms from its lattice points. That is why the imperfection is getting generated. Now, normally in a solid, there are thousands of crystals attached with each other. So imperfection is quite normal because it is densely packed with each other. But even if we are growing a single crystal, if we are talking about only one crystal, however care we take, whatever sincerity that is being measured, even then it is found out by researchers that there can be imperfections. So in this chapter, in this part of the chapter, we are going to discuss about those imperfections, which we call the imperfection in solids. We can also call it defects in solids. Now, we are going to talk about type of defects. Broadly speaking, there are mainly two types of defects. One is point defects, another is line defect. So as the term suggests, point and line. So it is very easy to understand what is a point defect. Point defect means missing or wrong arrangement in a particular lattice point. Means only at a point the some ions may be missing, or in place of that some other ions are occupying that. So only the problem is at a particular point, at a particular lattice point. What are those lattice points? In BCC and FCC and in simple cubic structure, in various type of arrangements, we must have already seen. Next is the line defects. Line, as the name suggests, it is not only about a particular point. Through entire row or column, the defect is present. That means it is not only about a particular point. The defect is throughout the solid, either in a particular row or in a particular column. So it is in a line, either it can be from left to right or from top to bottom. So these are the mainly two types of defects, but as per the syllabus, our main focus will be on point defects. Next is the causes for the point defect. Causes. There are mainly two causes. First one is missing, or you can say vacancy defect. And the second one is interstitial defect. So these are the two main causes for the point defects. It is the causes for point defect. Let us clarify. vacancy defect. So for that, let me draw a crystal, arrangement of a crystal. So suppose a crystal is like this. And for an example, here we are talking about the causes, not a particular defect. Suppose these are the plus charges. I hope it is clear. And there are some minus charges. This one. The vacancy defect may arise due to the missing of ions from any of these positions. Suppose this plus charge is missing, and suppose this minus charge is also missing, or suppose one of them is missing. If one of them are missing, then how to rearrange them, that is a separate cases. We will see the details of this just after that. But what I am telling is that if one of the plus charges or minus charges or both of them are missing, then it gives rise to the vacancy defect. Next one is the type of point defects. One is point defects in stoichiometric solids. One is point defects in non-stoichiometric solids. And third one is impurity defect. So let us start with this one first. Stoichiometric solids. Point defects in stoichiometric solids. Question is, what is this stoichiometry? What is that? Do you have any idea? Stoichiometry means the crystals, stoichiometric solid means rather the crystals having exact number of cations and anions as indicated by its molecular formula. What does it mean? Suppose there is AB. It simply means if there is one A plus, there will be only one B minus. So if there are 16 A plus, there has to be 16 B minus. That is how the stoichiometric solids are maintained. It's stoichiometry. So stoichiometric solids rather. So if in this type of crystals we are having any defects, and that too point defects, that is what we are going to discuss right now. So I have mentioned that point defects are of three types: stoichiometric, non-stoichiometric and impurity, among which I have first mentioned what is a stoichiometry, where the same number of cations and anions will be present as per their molecular formula. If it was AB2, that means for one cation there will be two anions accordingly. So let us talk about the point defects in stoichiometric solids. Point defects in stoichiometric solids are further bifurcated into two types. Carefully you remember this, it is very very important regarding the exam. First one is Schottky, check the spelling, Schottky defect, and another is Frankel defect. Named after the scientist. Schottky was a German scientist. He has invented or explored this one at 1930. And Frenkel is a Russian scientist. He has invented that one at 1926. Anyway, let us come to the point. First of all, Schottky defect. Schottky defect means when same number of cations and anions are missing from its lattice point or its original point. So let us draw it. Suppose this is how a crystal will look like. Here suppose these are the points, right? Now, in case of Schottky defect, suppose these are the plus charges and say these are the minus charges. And right now the crystal or solid is electrically neutral, right? Question is when same number of cations and anions are missing. Suppose I take away this plus charge and suppose I take away this minus charge. What does it mean? That here cation is missing and here of course anion is missing. And since one cation and one anion is missing, it will also maintain the electrical neutrality. It maintains electrical neutrality. So this is the important line. Same number of cations and anions are missing from its lattice point. So this is how Schottky defect will look like. Write it down. Next one is Frenkel defect. Frenkel defect means cation or anion is missing from its original site and located in an interstitial position. Let us see. It comes under the category of the interstitial defect. As I have told that vacancy defect and interstitial defect, there are two reasons of point defects. So let me figure it out first. There will be plus charge here, so it will be minus. So the minus charge will be here and the plus charge is here. Now, as per the definition, cation or anion. So suppose I take away this cation. So this cation is missing from its original site, as you can see. So let us mention it here. It is missing from its original site and it is present over here. So it is located in an interstitial position. This is called Frankel defect. Here also you see the number of cation and the number of anion is same. Earlier case, in the Schottky defect, same number of cations and anions were missing. So that is why they were maintaining the electrical neutrality. Here also the electrical neutrality will be maintained. The reason is, if one anion is missing from its site but it is occupying some interstitial site, so it is within the structure only. So the number of cations and number of anions will be same. After the point defects in stoichiometric solids, our next topic will be point defects in non-stoichiometric solids. So non-stoichiometric, the name itself suggests that the number of cations and anions present in the solid is not the same as it is described from its molecular formula. So in which cases it may appear? Let us take two examples. Suppose vanadium oxide. It is observed that it is not 1:1. If I keep the number of oxygen atoms X, it is formed that X can be varied from 0.6 to 1.3. Similar is the case with iron oxide also. Here also it is found out that it can be from 0.93 to 0.96. So iron can vary. It is not 1:1 exactly. So these are the examples of non-stoichiometric solids. Now let us see what are the classifications. Broadly of two types. One is metal excess defect, another is metal deficiency defect. We are going to talk about one by one. Metal excess defect means normally metal excess defect. Metal excess defect means normally the plus charge is more compared to the negative charges, means the cation will be more. So let us see some examples. So metal excess defect can happen due to two reasons. One is anion vacancy, and second one is extra cation occupying the interstitial site. So to prove this, we have to draw the diagrams. Let us talk about the anion vacancy first. Diagram will let you know what is the definition. We don't have to speak about it separately. Okay, so there are, say, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Let us do another one. It will simplify the job. Or suppose on here only we can do. So we are not talking about the anion vacancy. So let us keep it simple. First, it is A plus. Everywhere it is A plus. So the cation is A plus, okay? And the anion is termed as B minus. B minus, B minus, B minus. Here also, here also. So two things. Cation is A plus and the anion is B minus. I hope all of you have understood. So it is a perfect one right now. But anion vacancy means one of the anion is missing from its site. So what can we write? Anion missing from its site. This one. How the electrical neutrality can be maintained? It will be maintained because in place of anion, an electron will occupy the site. It will neutralize the plus charge, the electron, the negatively charged electron. So anion missing from its site, here just I am writing replaced by electron to maintain the very important one, electrical neutrality. Electrical neutrality. Okay, I hope it is very clear and the definition is given. So one anion will be missing from its site and it will be replaced by the electron just to maintain the electrical neutrality. So first you write it down, then on this diagram only we are going to discuss about the interstitial site. Pause the video and write it down. Now so this one is done. This was B minus. Here, see, extra cation occupying the interstitial site. So first thing first, let us put one extra cation. Any interstitial site, suppose this one. So extra cation is occupying the interstitial site directly. But it will give rise to extra cation, means extra positive charges. But the electrical neutrality has to be maintained. So to maintain that, what happens? One electron will be present. Electron neutralizes the excess plus charge, and it is also occupying the interstitial position. But why it is called metal excess defect? Because you see the number of plus charges, number of cations rather, 1, 2, 3, 4, 5, 6. But here it is 1, 2, 3, 4, 5 only. So the number of cations will be more compared to number of anions. That is why it is called the metal excess defect. So we have seen two types of metal excess defect. One is by one was by cation anion vacancy and another is extra cation occupying the interstitial site. Next one will be metal deficiency defect. I'm just keeping it as it is so that from here only we can express. So metal deficiency defects, like the metal excess defects, are also of two types. One is cationic vacancy. Second one is extra anion occupying the interstitial site. Very easy because we have already seen the previous cases. Metal deficiency means the number of anions will be greater than the number of cations. See, 1, 2, 3, 4, 5, 6. Right? Here also it is 1, 2, 3, 4, 5, 6. So 6 cations, 6 anions now. Perfect. Now cationic vacancy. If one of the cation is missing. Okay, so one of the cation is missing here. Cation is missing. But how to maintain the electrical neutrality? Surprisingly, one of the cation in between will occupy extra charge. One cation carrying extra, that is +2 charge on it. So now you calculate the number of cations. It is 1, 2, 3, 4, 5, but anions 1, 2, 3, 4, 5, 6. So more anion than cation, that is why metal deficiency, but it maintains the electrical neutrality. Write it down. Next one is extra anion occupying the interstitial site. Before that, let us fill it up as it is. Now, extra anion will occupy the interstitial site. So, this is the extra anion, B minus. Is the extra anion occupying the interstitial site? This one. So, how to maintain the electrical neutrality? For that, like the previous case, one of the cation, suppose this one once again, will carry extra positive charge. So, one of the cation carries extra positive charge to maintain the electrical neutrality, of course. Now you see 1, 2, 3, 4, 5, 6. 6 cations, but anions 1, 2, 3, 4, 5, 6 and extra 7. So that is why it is called metal deficiency defect. The last one is called the impurity defect. After this was the second, there is a third one which is the impurity defect. Let me draw the diagram only because it will let you know what is the impurity defect. Suppose we are drawing one NaCl crystal. So consecutively there will be Na plus and Cl minus. So Na plus and Cl minus we have to write. So Na plus alternatively and in between there is Cl minus also. Suppose one of the Na plus is missing. So Na plus is missing. How to maintain the electrical neutrality now? One of the Na plus may be replaced by another cation, that is strontium 2 plus. So Na plus replaced by strontium 2 plus. Since strontium is having extra positive charge, so to maintain the electrical neutrality, one Na plus has already left the position. So here the cation is actually replaced by another cation, which is something new. That is why it is called the impurity defect. So we have discussed all the defects, imperfection in solids. Our next topic and the next video will be based on a different topic, which is known as the semiconductors, absolutely new concept. So first we need to understand the imperfection in solids. You read it out, practice the diagram. Remember, whatever question that will come from this particular topic, you have to draw the diagram only. Through diagram only the explanation will be much better. So that you have to do. So whenever you draw it, draw the diagram big and fair enough for the examiners to understand.